Never done it.
Distance.
He's doing shot put.
I'm absolutely not.
They do javelin.
See these?
You do javelin.
The poles are small.
Dude, my friend Austin Schultz,
Yeah.
he's running 7 miles today.
Yeah, that's what I did on Saturday.
I can barely run a mile.
I get tired of driving 7 miles.
Virginia, that is so
Running it is
relatable.
more enjoyable. Running it is more enjoyable.
If
Wow.
you're into painting,
If you're into not being able to breathe for 3 hours.
yeah, that's
No, you want to do that swim.
okay. All right, so let's chit chat about the lab, okay? And it was odd, and that, especially that first one with that strontium hydroxide, and that's a little sketchy. That's the one that's kind of the least soluble, and depending upon your molarity, it's classified as like moderately soluble. And I thought I had high enough concentrations where you should have gotten precipitate, and some of you did, and some of you didn't. So that got a little bit sketchy. But here's the main thing that I want you to see. So when you get to that second question on the back where I say, hey, make like a diagram, okay? So here's what I want you to see with that magnesium hydroxide. This is kind of what I'm looking for. So you got this precipitate of magnesium hydroxide, right? And up above, and don't, again, I tell you this, do not focus on the precipitate. Focus on the solution of what's up above, okay? That's the whole key to this. So up here you've got some magnesium ions and you have some hydroxide ions because Mother Nature is trying to produce some combination of your magnesium ion concentration times your hydroxide ion concentration, okay, squared. So you have a certain equilibrium, and Mother Nature is cool, right? It's like it's happening, right? Now, you begin to add hydrochloric acid to it. And this, again, don't focus on the chloride, because the chloride isn't going to do anything because it's not a common ion to anything. The chloride's just there. It's just kind of along for the ride, okay? But the focus is going to be on that proton, that H+. So this hydroxide comes along and it sees that proton and it goes, oh, let's make, wait for it, a little Spanish, el agua, okay? If I'm teaching this in Setswana, I would say, oh, let's make some pula. If I'm teaching this in Nicaragua, I'd say, let's make vula, okay? So your main point being you're going to make water. So you're going to decrease the concentration of the hydroxide ions. Mother Nature at this point flips out and goes, oh, this is bad, okay? I'm losing hydroxide ions. So what's the only source of hydroxide ions Mother Nature has available to it?
The precipitate.
Yes, so it's got to take that as a precipitate and dissolve it out, okay? So all I'm looking for is that you realize, hey, there's a whole bunch of magnesium ions, there's a whole bunch of hydroxide ions. Then in the second one, just realize, oh, there's a smaller number of hydroxide ions, but now I've made water. So the hydroxide ions are still there, but now they've bound up with the proton, so that's dropped the concentration of the hydroxide ions. The precipitate dissolves to try and maintain that KSP value. Now, because of the fact that it's dissolving, you're also increasing the concentration of your magnesium ions because that MgOH2 is dissolving. So you're actually increasing the concentration of your magnesium ions as well because you just can't go to the precipitate and go, oh, we're just going to pull out hydroxide ions and we're going to leave the magnesiums alone. Okay? It has to dissolve in that ratio of 1 to 2 where you get 1 magnesium and 2 hydroxides. Okay? So this is why that precipitate dissolved was because of the fact that you were decreasing the concentration. So when you see something dissolve, okay, when you add an acid, the only way that thing is going to dissolve is if the anion is going to bond with the proton to form either a weak acid or water. Okay? Those are the two situations where you're going to make something dissolve. Okay? Cool with that one. All right. Is there anything specific one you want me to go over?
Can you go over 10?
The ones that's more soluble? Okay. So let me see your paper. Okay, so on number 10, here's the deal. So you got lead carbonate, AgCN, and nickel bromide. Okay? Thank you. So those are your precipitants, right? So what you want to focus on is, let's say that you have lead carbonate. So you have a precipitate of lead carbonate. So that means you have some lead ions up here, and you have some carbonate ions up there. Carbonate is 2 minus, okay? So it wants to reform carbonic acid. So if you're not sure, look down your list of weak acids, okay? Oh, carbonic acid, that's a weak acid. So being a weak acid, it has a relatively strong conjugate base. So when I dump protons in here, that proton is going to bond with that carbonate. You're going to form carbonic acid. You're going to drop the concentration of your carbonate ions. The precipitate is going to dissolve. Okay? The same thing is true of silver cyanide. Cyanic acid, HCN, is a weak acid. Okay? So that means that CN, when you add protons to it, you're going to drop the concentration of your CN. The precipitate is going to dissolve. Now, but you look at nickel bromide, okay? Now, at this point you should know, oh, hydrobromic acid is a strong acid, right? So if I dump protons in there, are you going to reform hydrobromic acid? No, okay? So the bromide is going to say, hey, I'm happy that you're here, Mr. Proton, but we're not going to hook up, okay? We're attracted because we're oppositely charged, but we're not going to form the molecular form of the acid, okay? So what you could do, and this is called differential precipitation, is that let's say that you had a precipitate down here that was a mix of, say, lead carbonate and nickel bromide, okay? Let's say that you had a precipitate that was a combination of these two, okay? Lead carbonate, nickel bromide. You had a combination of these two. And you add nitric acid or you a strong acid to it. So if you add a strong acid to this, the nickel bromide won't dissolve because the bromide isn't the conjugate base off of weak acid. The nickel bromide is just going to chill out, okay? Now, the lead carbonate would dissolve. So what you would see in that solution up here is that you would see the lead carbonate dissolve, so that would go into the solution. The nickel bromide would remain as the precipitate. So that's how you can separate two different precipitates. The one that has an anion that's soluble is the one that's going to have an anion that's the conjugate base off of a weak acid, and that's what's going to dissolve. Okay?
Yep.
Now, you couldn't do that, like to separate lead carbonate and AgCN. You couldn't separate those two because they're both would become more soluble in an acidic solution. Okay? On number 8, every answer on number 8 should start with an 8. And you should see that the exponents range from -2 to -12. On number 11, both of your answers on 11 should be 10 to the -7th.
Can you go over 11B?
11 what?
11B.
Yeah. Let me see here. So on number 11, so you got copper nitrate, determine molar sodium, okay. So here's the whole key to this, is that if you look at how that KSP is calculated, which is your copper ion concentration times your hydroxide ion concentration squared, right? Okay? So this is going to become x, this is going to become 2x, but that's going to become squared, so you get 4x cubed equals your KSP, right? So this is what Mother Nature wants, okay? Mother Nature wants, mathematically, this combination to produce that KSP value, okay? Now, you're not given the copper ion solution, you're not given the hydroxide concentration, anything like that, so you just have to assume that it ionizes in a 1-to-2 ratio. Okay, that's all you can do. Now, the whole key to this is that you're going to get an answer of 2.3 times 10 to the negative 7. That should be your answer to 11a. 2.3 times 10 to the negative 11, to the negative 7. Okay? Right? Okay, that's it. Now, the whole key to this is that I'm going to double the volume. So imagine, here's this test tube, it has a certain volume to it. I'm going to add water and I'm going to double the volume. But what you're told here is that some of the precipitate still remains. What that means is that that solution up above is still in equilibrium. Okay? Now, did some of the precipitate have to dissolve to maintain that same molarity? Yes. Okay? So your answer to 11b is the exact same because it's still in equilibrium. And this is what you have to understand. This is molarity. Okay? It's molarity. So that's what this number represents, is moles per liter. So as long as it's still in equilibrium, that's still 2.3 times 10 to the negative 7. Okay? Now, if it all dissolved, then you couldn't answer the question because it dissolved. You don't know if it just reached an exact equilibrium point or maybe it's not saturated at all and you can add more to it. Now, Amanda, the opposite would occur, okay, is if I took this test tube and I let it sit out for like a week and some of that evaporated off and I decreased the volume by half, that concentration would still be 2.3 times 10 to the negative 7. But you'd have to make more precipitate because of the fact that you're decreasing the volume. So here's the deal. As long as you see a precipitate, whatever that concentration is up there is just going to stay the same. Okay? Which one?
Number 4.
What's number 4?
The solution paired with results in the formation of silver chloride, PBT, what if any
Okay.
changes?
So, number 4?
Yeah. Or this is-
Okay. Okay, so this thing is trying to ionize into silver ions and chloride ions, right? So up above that precipitate, you got silver ions and you got chloride ions. Now, specifically, I'm going to add hydrochloric acid, right? So I'm going to add an ion that's common to what's up above.
So it's one
So what's Mother Nature going to do?
more precipitate.
Yeah, because you're adding an ion. Now, if I added like nitric acid, nothing would happen because I'm not adding one of those common anions, and chloride is the conjugate base off of a strong acid. Okay. On number 7, that first answer should be something times 10 to the negative 3rd. B should be 10 to the negative 12th, and C should be 10 to the negative 5th. Anything else?
So 7C was 10 to the negative 5th.
Yep.
I think I did something wrong.
Me too, too.
Okay, here's the deal, right? On this one, you've got x, and then you have 3x cubed.
Yep.
So on 7C, you've got the molarity of that 0.150. So this is becoming 3x cubed.
Okay. Okay, that's what I did now.
Okay, you were erasing, I swear to God, I thought we were having an earthquake.
No, sorry.
No, because I was leaning on here,
Oh,
and it was shaking. It was like, oh, what's going on?
My
So, it's all right.
my bad.
It's okay. It's all good.
I'm glad.
All right, anything else? Going once. Going twice. Last question at all. Sold. So make sure, number one, that there's no frizzies, okay? Annoy me, okay? And make sure that you kind of kept everything kind of organized so that I can kind of follow along. So just staple that, the lab itself to the front and get that handed in. So,
We can turn this over the other class, right?
oh yeah, I don't have to have it right now. And I'm not going to talk the whole time. I'm going to
Okay,
give you
good,
time
'cause
to
I
either
need-
finish up this lab or work on the review. So, okay, stop that camera for a second. This is what you've got to be able to do, hopefully without giving this a second thought, okay? So let's say I want to give you 100 milliliters of a 0.2 molar solution of formic acid. Ka is 1.8 times 10 to the negative 4. Now, Ka of acetic acid is 10 to the negative 5th. So is formic acid a stronger acid or a weaker acid than acetic acid? Why?
Because its Ka value is higher, so that means that ionizes.
Beautiful. So you got to say, wow, look, that has a bigger Ka value. The only way I can get a bigger Ka value is if it ionizes more. Okay? So it's going to be a stronger acid, but it's going to have a weaker conjugate base. Now, if you compare that to an acid that has a really, really small Ka value, like 10 to the negative 10th, then this would be a stronger, much stronger than one that has a much smaller value. Okay? All right. So hopefully this first one you should be able to do without any thought. I want to find the initial pH of a 100 milliliters of a 0.2 molar solution of formic acid. So first off, are you going to worry about any hydroxides at all? No, we've not added any base. This thing is just sitting there chilling out. Okay, there's no hydroxides involved. Don't make this complicated. Here's your reaction. HA is going to yield hydronium plus your anion. It's a non-buffered solution. We haven't added any formate ions. It's just 0. Oh, okay. Here's 0.2. Here's 0. Here's 0. Minus X, plus X, plus X, X. Now, I'm going to tell you right now, on the test, you are never going to have to worry about subtracting this X to the point that you have to work a quadratic. Okay? You will not have to do that on the test. I know you math nerds are going to be a little bit disappointed, Noah Hale, but you're not going to have to work any quadratics. Okay? This X is always going to be small enough where it's not significant that you have to mess with it. Okay? All right. So, you've got the Ka is going to equal X squared over 0.2. The Ka was, and I just made this problem up, by the way, times 10 to the negative 4th times 0.2, so works.
0.006.
That's my X value. 0. What?
006.
Exactly? Wow, I'd like to say I had that worked out. So that's the concentration of my hydronium ion, so I have a pH of 2.22. Okay? So, my pH curve is going to start here at 2.22. If this had been a strong acid, if it had been a strong acid, how would I get the initial pH? If it had been a 0.2 molar solution of a strong acid.
Negative log of the concentration.
Yeah, I just have to take the negative log of 0.2 because it would fully ionize. Okay, if it had been a strong acid, I just have to take the negative log of 0.2, which would have put it as a higher or lower initial pH.
Lower.
Lower, because you're taking the negative log of a bigger number. Okay, so that's the dichotomy. Negative log of a bigger number produces a lower pH. Okay. Now, if this had been a buffered solution, okay, if it had been a buffered solution where I had some of that formic ion in here, okay, then you do the Henderson-Hasselbeck equation, and this concentration here, when you get that X, if it had been a buffered solution, would this X have been bigger or smaller than 0.006?
Smaller.
Why, Works?
Because if you raise your anion concentration, you have to lower your H plus concentration to keep equilibrium.
Beautiful. Fantastic answer. If this had been a buffered solution, I still want the exact same Ka value. My anions would go up, my hydronium ions would go down to produce the exact same Ka value. Okay? So my pH then would have gone even higher. Okay? Got that. Okay. So, we got a pH starting here at 2.22, right? So that's where my pH is going to start. Now, if you were to look at a graph of the molecular form of the acid and the anion, okay? Which one's, why is the molecular form going to start really, really high and the anion start really, really low?
Because you have no anions when you start.
Yeah, okay? And it's not going to ionize, it's going to ionize some, but not very much. So this is going to start really, really low, okay? And my formic acid, the molecular form, is going to start really, really high. That's the whole point. That's what makes it a weak acid, okay? So as I add base, what's going to happen to the concentration of my formic acid? It's going to decrease, but the concentration of my anions is going to increase, okay? So this graph is going to go something like this, right? So I'm going to drop the concentration of my acid, I'm going to increase the concentration of my anions. When those cross, how much have you neutralized?
All of it. Half.
Half of it. Okay, this is when it's going to be half neutralized. Because I'm going to have equal concentrations of my acid and equal concentrations of my anion. When it's half neutralized, where's your...
My bad, I think that's mine. I swear to God, I put it on silent. I don't understand how this happens.
Do you have a tile?
The tile sound.
Oh, it is?
It's a tile sound.
Oh, no. I apologize. I guess I sat on my keys or something.
You're kind of methyl red right now. You've turned acidic. Okay. So,
Give them a base.
Give them a
give him a base. All right. So I'm going to add 100 milliliters of 0.1 molar sodium hydroxide. Okay? Now I want to know what the pH is. So what's the first thing that I'm going to expect you to write out?
HA plus NH equals H2.
Yeah, if you don't know what the reaction is, you're screwed. Okay? So you're going to get water and the anion, right? So I started with 100 milliliters of 0.2 molar solution of the acid. So if I take 100 times 0.2, I get, so I've got 20 millimoles of my acid. And on the test, tomorrow, make sure that I know what you're working in. Are you working in moles? Are you working in millimoles? Are you working in molarity? Okay? Just don't write down numbers because I'm going to have no idea what you're doing. Okay? Write down what they are, because there's a huge difference between millimoles, moles, and molarity. So don't write down numbers and go, oh, Bergkamp will figure it out. No, Bergkamp won't figure it out. Okay? Make sure I know what you have done. Okay? So I take 100 times 0.1, I get 10 millimoles. So it's a non-buffered solution. My anion starts at 0. So, Peterson, how much of this stuff have I neutralized? Nope. Half of it, right? I've neutralized half of it. So because of the fact that this is a weak acid being titrated with hydroxide, when you have neutralized it, what is your pH equal? Your pKa. So, in this case, my Ka value is 1.8 times 10 to the negative fourth. So if you use the Henderson-Hasselbeck, which I recommend, plus the log of your anion concentration over the concentration of your acid, that's going to be 10 millimoles, that's going to be 10 millimoles. Now technically, remember, you are dividing by 200 milliliters, okay? Because you're technically, this is molarity. Technically, you divide by 200. but you're dividing both of those by 200, so it just cancels out, so you can just take the ratio of millimoles. Now, if you're hardcore, it's like, I gotta have molarity. I'm happy for you, okay? If you really want to take each one and divide by 200, knock yourself out, okay? It's gonna be a waste of time, you're still gonna get the same answer, but if that's in your wheelhouse, hey, go with it, okay? All right, so what'd you get?
3.74.
3.74. Now, half neutralized, pH equals my pKa, right? So at this point, I am half neutralized. At this point, my pH curve has climbed up to 3.74. Okay? Boom, we got it. We're good. Okay? So, if you were to look at, and this is important that you understand, at this point, the concentration of my acid, because if I take this and divide it by 200, and if I take this and divide it by 200, I'm going to have equal concentrations. So prior to this point, I had more acid than I did anions. After this point, I'm going to have more anions than I have acid. Okay? So there's this break point. Okay? Now, the pH at this point equals my pKa, which is 3.74. Would I want to choose formic acid if I wanted to prepare a buffer solution of, say, 6?
No.
Why not, Words?
Too small.
Yeah, okay, it's too far away. Okay, if I want a buffered solution of 6, I don't want to choose formic acid because I'd have to make it shift too far. Okay, remember, when you choose a buffer, you want to choose one that's pretty close to the pKa. You can use this part to tweak it. Okay, so like if I wanted to end up with a pH of 4, okay, hey, I could use this part to tweak this to get it to 4. Okay? I'd have a higher concentration of my anions and a lower concentration of my acid because I want to take the log of a value bigger than 1 so that I can add it. I can get that to 4. If I wanted a pH of 3.5, I'd have my anion concentration less, I'd have my concentration of my acid higher, I'd be taking the value of a log less than 1, that would end up being a negative value. Okay, so that's what you want to be able to think through. Okay? All right. Now, at this point, I'm going to add another 100, so now I've got a total of 200 milliliters of 0.1 molar sodium hydroxide. Okay? So this is going to be HA plus OH yielding water in the anion. So I got 20 millimoles, 0, minus 20, minus 20, plus 20. Now, if this had been a strong acid, like nitric acid, titrated with sodium hydroxide, what would the pH of the solution be? 7. It would be 7 because if it was nitric acid, that nitrate would not react with the water. If it was hydrochloric acid, that is not going to react with it. Okay? I'm not saying this anion isn't there. It's just not going to react with the water. That's what makes it a strong acid. Okay? So if it was a strong acid, strong base, pH is 7, boom, you're done. Because there is no secondary reaction. However, party girl, what are we going to have to do?
Second reaction.
Beautiful. Someone had the anion reacting with water. Party girl, what do I get out of this?
HA and OH minus.
Beautiful. So now I'm going to start to form hydroxide ions. So once I start to form hydroxide ions, Matt, what's going to do to that pH? That's right, because I'm generating hydroxide ions. So at the equivalence point, my pH is going to be above 7 because I'm generating hydroxide ions. Now, what do you have to do with those 20 millimoles? Can you put, on this new rice chart, can you put in 20 millimoles here? No. What mindset do you have to be in?
Molarity.
I got to be in the molarity mindset, okay? Not the millimole mindset, not the mole mindset. I got to be in the molarity mindset. So again, you got to change your mindset. Up here, we're working in stoic. we were in the millimoles and mole mindset. Here, I've got to work in the molarity mindset. So I'm going to take 20 and divide it by what? What's the total volume? 400 milliliters. So we're going to take 20 and divide it by 400, get like 0.05. 0.05?
Yeah.
Okay? That's my molarity. Boom, 0, 0. Minus X plus X. I get X, I get X, I get 0.05. But, now what do I have to use? I got to get the KB value, but Bergkamp's a jerk and he didn't give me the KB value.
Problem's over, I guess.
That's it, we're done. Screw it. We're on strike.
I'm done.
I've had enough. Can't work in these conditions.
Good luck with that. I don't, hey, it makes it easy for me to grade. It's like, I'm just not going to work the problem.
That's
Okay.
what our mind
It's
said.
like, really? Okay.
I'm leaving the building.
You know how easy that is to grade? Okay. So what are you going to do?
Divide 1.00 e to the
Divide the
negative
auto
14.
ionization constant of water by your Ka value. That's going to get you your.
KB value.
So Kb is going to equal.
5.56 e to the negative 12.
So the Kb was what?
5.56 e to the negative 12.
Times 10 to the negative 12. I'm going to multiply that by 0.05. Through that, and that's going to get me my hydroxide ion concentration, which is what?
5.27
Should be 11.
E to the negative 7th. So then you get a POH of,
6.28.
and you get a pH of
7.7.
7.72. If you get done with the test and you have not done a problem like this, you have done something horribly wrong. Okay? I'm going to tell you this right now. If you hand in the test and go, wow, I never found a KB value, something bad has happened.
Go sit back down.
Because I left.
Well, that's true. You just handed it in. You said, here, Bergkamp, I'm good. And you
No,
just handed the test
you
back.
handed it to him, and then he handed it back to you and said, "I'm good."
I'll find a way to work around and not use KB somehow.
Okay, well,
Yeah, that
That-
data was a little bit wrong. It should have been, the KB should have been to the 11th, I think.
No.
It doesn't change it.
No, you're wrong.
Really?
Changes it by
Bodie
one.
agreed with me. What?
Changes it by one.
because the Ka is 10.
Oh yeah, you're right. Sorry.
Words.
Sorry.
You're both good.
I'm sorry.
Okay, so what is it? 10 to the negative 11th?
Yeah.
Yeah.
So the OH is then
5.78.
it's okay, words. It's not a big deal.
Not a-
So the OH is what? 5 point what?
7.8.
Times 10 to the negative.
No, that was the PO.
Oh, sorry.
The OH is
Spoiler.
1.66 times 10 to the negative 6.
Hold on. Back up the bus.
Yeah.
What's your hydroxide ion concentration? 2.78 times 10 to the negative 12. So your POH is, that's your POH?
11.56.
No, okay, I got something else.
I like Riley's
Something's
Hey, I
horribly
screwed this
wrong.
up.
I like Riley's answers.
That's not, that can't be your hydroxide ion
Let me do it
concentration.
again.
The 1.67 times 10 to the negative 6.
Yeah, that's
Yeah.
what
I like that number a lot
I
better.
concur.
Yes.
So what you get is your hydroxide ion concentration?
square root.
Oh,
we're not taking the negative 6.
Yeah, I got
I
that.
didn't realize that's what that
I
meant.
don't like that number. It gives me sinister thoughts.
And then your POH.
It what?
Nothing else.
And
POH is
So your POH is what?
5.78.
That sounds better.
So your pH is
8.2.
8.22.
8 point what?
2.2.
8.22.
My bad, guys.
We're good.
I mean,
We
everyone
had
else
the
messed up
process.
Riley's.
I'm doing the math on
What'd you say, Ryan?
Everyone else messed it up.
That number is so.
True.
Okay.
So it's not just me.
It's a vocabulary.
So
All right.
it's straw.
No, this is. It's quite feckless, if I understand.
I can only think of the two with some of the being
It's quite
called
organic.
That's the only thing I can think of when I hear the word pet version.
Bodie, did you get number 7 right? Because I didn't.
What was your answer? No, I have a number. Which film of belief did you
I need to work on it. It wasn't right.
Weird.
Look at
that was what I
the
did
only
last.
one is that I could find the thing with the hills. The rolling
I have it installed for the next
Flint and
Not the
Rolling Thunder, there's a.
there was no, that wasn't.
Okay,
It is green.
so let's say I gave you this problem.
Something else that makes sense.
You have water, I'm going to take some solid magnesium hydroxide and I'm going to add that to it. And I'm going to add it to it until I see a precipitate, and that way I know it can't dissolve anymore. So I take a pH probe, I place it in there, and I get a pH of 8. So based upon that information, I want to be able to calculate the KSP of magnesium hydroxide. So, go. Let's say this is the problem on the test.
Oh, God.
Okay.
I'll look at that later. Thank you.
Ooh, then Aiden doesn't have to do it.
Yeah, Aiden just turned his test in, so he's okay.
Yeah, you're done.
Can't grade it, there's nothing to grade.
Oh, yeah.
I'm literally doing this right now. I'm just gonna do.
Whoa.
I think I still did better than Kate, even though I didn't do nervous.
It didn't do any of it?
Now, if you want to start the test early tomorrow, okay, if you want to come in like at 11:30 after you get that evening lunch, if you want some more time to take the test, I'll let you start it as early as 11:30.
Aw, you're so kind.
No, very smooth. I have the number.
No, mine is 1.4.
What do you get?
No, this is for.
That's just wrong. Did
You want to find the KS. I got
Do
you.
you want to calculate?
I got
the
you.
KSP?
Got you.
Oh,
Maybe an intersection.
Interesting?
yeah.
Why?
I think I'm right. I'll give myself a.
Hey, we're just gonna try this, and if it doesn't, if it's not right, this is why we're reviewing it.
Because look, okay,
This is
the
trackless hills of Flint, Kansas.
because look, there was one that I put it.
Can you give me a ballpark for here?
I don't know, I just made up the problem.
Oh, okay, cool.
And like,
Yeah, then
So, I don't know.
That
Dang.
makes sense. Because
if my ballpark,
Yeah, I kind
if
of
it's
did.
like way out of the
Yeah.
ballpark.
I'm guessing around, if I were to just pull out a number, I'd say 10 to the
I
negative
think it was feckless.
10.
yeah, that
And,
makes a lot of
shoot, I did
No. She asked me to just make up a number. I just kind of estimated it.
Yeah, but mine is still.
I don't know what the answer is,
Still
okay?
very, very far.
And that could be way off too,
Tate, what's your answer?
okay? My mental math is a little sketchy.
No, I got 5 and negative 19.
I got 5e to the negative 19 too.
That's what I.
Okay,
Oh my god, I got the same answer as the smart kid.
okay. So what do you have to have first?
Concentration.
Kid,
Oh, wait.
No,
I'll give you that reaction.
yes.
You don't need to react. What?
He's gonna kill you.
Oh, you haven't seen her get close to wanting to kill someone?
Really? Burkham's pretty mellow.
No,
You haven't been here when
he's
you
seen it.
haven't been here
Was
when
it
he's
you?
crazy.
No,
I guarantee you
Back to
that
the last year.
yeah,
Last year.
yeah.
this threshold.
You're chiller this year.
Oh, yeah. No, and you didn't see when he was, I had him as a junior.
Oh, yeah.
And I had 2 girls that would sit right here, and literally, they would say, "Don't kill him, it's not worth it." No, seriously, they would reach out and grab my hand and
Was it
go,
Fong?
"Don't kill him."
Remember that one kid tried to like fight you?
Last year?
I think they're right. It's not.
Yeah, okay, yeah.
Okay. Nope,
Nope, no drama.
I wanna know.
nope,
I wanna know the drama.
okay, no, he was a great kid. We just, every once in a while, it's just like, oh my God. Okay, so, this is gonna ionize into X and 2X, right?
No.
Yes.
Okay, it's 2-to-1 ratio, right?
Yeah.
So knowing that you have the pH, what can you find?
POH.
You can find the POH. Once you find the POH, you can find the
OH concentration.
you can find the OH concentration, which is what?
1.20 to the negative 6. God.
1 times 10 to the negative 6th, right? Now, here's the question. Is my magnesium ion concentration twice that value or half that value?
Half that value.
Half, because it's like a 2-to-1 ratio, right?
Yes, sir.
So my magnesium ion concentration then is 5 times 10 to the negative fifth, right?
Right.
So then my KSP is going to be my magnesium ion concentration times my hydroxide ion concentration, but what do you have to do with that? Square it, so what do you get? 5 times 10 to the negative what?
19.
Negative 19.
Woo-hoo.
Okay? Cool with that.
I figured out what I did.
Bird camp, I did it. You should be so proud, because I was not doing
This
problems.
is a victory.
Okay, so if I gave you this list, fluoride, anion, water, fluoride ions, and if I said, I want to know which one is the weakest conjugate base and which one is the strongest conjugate base, ranking them in that order. Strongest conjugate base to weakest conjugate base. Now, fundamentally, what am I asking for? The ability to what? Not ionize, just the opposite.
Go back to that.
I want you to rank them in order of basically the one that is most, that's what we're talking about, is the ability to pull in protons, right? Okay? So here's my question. Of those three, which one's going to be most willing to pull in a proton? The fluoride, the chloride, or the water? Fluoride, why?
Is this a conjugate base of the?
That's the only one that's a conjugate base off of a
Weak acid.
weak acid.
Specific vehicle.
So your fluoride ion is going to be of the most willing to pull in the protons. Okay?
And then the chloride?
No. No.
Or I just don't want to do.
Okay? Now, you put hydrochloric acid in water. What's it going to change into? Hydronium ions and fluoride ions. This is a tug of war, right? The water has the positive end of that water molecule and the negative end of the water molecule, because that's what makes water such a cool solvent, right? So this water molecule is going to be, the negative end of that water molecule is going to become attracted to that proton because they're oppositely charged. So here's the deal. So this water is tug of war. This water has a stronger pull for that proton than the chloride ion does. This is what makes it a strong acid. Okay? So your break point on this list is always the water. Okay? So the water is going to be more willing to take in a proton than the chloride ion is. That's what makes it a strong acid, because that proton is going to be at a lower energy level with the water than it is with the chloride. Because if that proton was more comfortable at a lower energy state with the anion, guess what? It would be a weak acid. Okay? Now, here's what I'm not going to make you do on the test. I'm not going to make you write out the names and the formulas. Okay? But you're going to have to know the strong acids. Because I might give you something like this and say, okay, you have a precipitate of, I don't know, strontium, carbonate, and AgCl. Okay? So you have two precipitates, strontium, carbonate, silver chloride. And I'm going to add a strong acid. Which one of these is going to dissolve in that strong acid? The strontium carbonate or the silver chloride? Why?
Because it's the conjugate base of the
Yeah, the chloride ion is floating up here. It's going to care less about that proton, okay? Because it's a strong acid. So this is where you're going to have to know this. Now, I'm going to tell you this right now. So help me on the test, and I've just had this happen because you all get stressed on the test, okay? And I've had this happen, especially like someone asked this really out loud, and it's just painful, okay? Like if you're working with, say, nitric acid, don't go, Mr. Burkamp, we don't have the Ka of nitric acid, okay? And they ask that out loud, and they like accuse me of screwing up because I didn't give them the Ka of nitric acid. and then everybody else goes, okay? So what will happen on the front of the test is that I'm going to give you every Ka value for every weak acid that you're going to need throughout the test. Okay, that's going to be on the front page. Okay, that's going to be there. If you don't have a Ka value, don't go, Burkamp, you screwed up and didn't give us the Ka value. Don't. I'm telling you now, don't. Okay, because everybody else is going to be going, okay. So I'm just telling you, don't do that. Okay, so I'm done. So here's what I'm going to give you. No, this is not due. Okay, it's not due. So you've got, basically, it's a 2-page review. Okay, a whole bunch of questions. If you can do this and feel good about it, the test will probably go okay. Now, this isn't everything that's going to be on the test, but it's most of what's going to be on the test. Okay. So the test is going to be a bunch of, it's going to be like this. You're going to have a bunch of stuff that you're going to have to work out. There will be some multiple choice questions, but not a lot, mainly because this is pretty much a series of calculations. There's going to be KSP and QSP questions on it, okay? So what do you, if you're going to form a precipitate, what do you know about QSP relative to KSP?
That'll be the same.
It's bigger.
It's bigger, usually by about a factor of 1,000, okay? Now, and go back and work through the labs. If you double the volume of, when you mix it, if you double the volume, what happens to the molarity?
It has.
It becomes half, because you're taking the same number of moles and you're dividing it into twice the volume, okay? So, remember that. All right. So I am done. Stop that.